Hey, my name is John Haltiwanger, also known as Abstract, and I'm here with my presentation entitled Mind-Bending Moments in Hacking RakuAST. When I first wrote the description of the talk, I may have been a bit ambitious. I tend to do that. Um, so one apology I can make straight out of the bat to the description is I couldn't scope everything I wanted into this presentation. So unfortunately, we will not be doing direct comparisons to the base implementations. Not only is it quite hard to get a proper screenshot that provides adequate context within the Perl 6 actions and grammars modules, the discussion of previous behavior is really ancillary to the goals of this talk. Um, yeah, so the aims of this talk actually are to hopefully help demystify the process of hacking RakuAST, present a little bit of my recent work in it, and yeah, I just wanted to say at the outset, it's quite opaque until it isn't, and then it is again, and then it isn't. So it's a kind of cat and mouse game that can be actually be kind of fun and satisfying in its own right. Um, but yes, if you've ever wondered what it's all how it all works, hopefully I can help a little bit with that. So we're going to do a little brief overview of RakuAST. Some setup tips that I find really helpful for developing and the implementation of once and the implementation of first. And then a little outro with the caveat that if we have extra time, I do have some extra stuff that we could cover. So let's get going. So what is RakuAST? RakuAST is a total rewrite of the compiler front end. So what that means functionally is that it's a high level interface for generating low level runtime instructions. And that's you get to write in a RakuAST flavored NQP that feels quite natural after a little while. And then when you get back to regular coding in Raku, you get to appreciate all the hard work that's been done to give you such expressivity in the full language. So that's always nice. Um, a note: the RakuAST flavoring is around the type system, as RakuAST node implementations need to be classes in the Raku type system. So it's not like some sort of underlying NQP sort of thing. It's you're writing the code in under the constraints of NQP, which are actually, I mean, you even get your method call syntax with colons and everything. It's pretty expressive, so nothing to worry about there. I really like the way that Jonathan Worthington described AST as a document object model for a programming language, and it's also the latest in a series of three-letter refactors throughout the history of Raku. So there was the new object model, or NOM, the Great List refactor, the Great Hash refactor, which fittingly, given the presence of hash, folks were a bit fuzzy on the details of this one. And now the AST, or Abstract Syntax Tree, or fully titled RakuAST refactor. From the documentation, the goal of RakuAST is to model things at the language level without normalizing too strongly. So basically the opposite of the cast design goals. So in some ways, RakuAST can be seen as a tension of opposites. In the end, these RakuAST nodes just generate cast. So they're dealing with this very with this very strongly normalized syntax, but the goal is to pull the level of modeling back as far from the cast representation as possible. So it leads to some interesting dynamics. This turns out to be quite far indeed, actually, in terms of how far you can go back with the modeling in some cases, but we'll get to that. So advantages of RakuAST, like the separation of behavior at various compilation stages within the same node code. So I haven't actually looked inside of some of the working, like I don't have a full grasp of how the base compiler works, but after dealing with RakuAST, it's really hard to look for behavior in the base compiler sometimes because of how fuzzy the separations are between certain things, and how you can usually find what you're looking for eventually, but to get your mind wrapped around it is something else. So by generating cast as late as possible, we are able to do stuff like assemble meta objects and create the conditions for the cast to be prepared in a way that doesn't have to reference back from any intermediate state. So the clarity around what happens when without too much bookkeeping, sort of how I was a phrase that came to mind when I was thinking about this. So this maybe will help a little bit in understanding how the base compiler generates its cast. We have a grammar that parses and calls, then methods and actions are called. And on matches. But you have these feedback loops between actions and this what's called the world object, which is obviously, yeah, this is defined by a class. I don't know too much about it besides, it to declare a package, you need to talk to the world to get your context and your reality together to start building the cast in a comprehensible way. And so you kind of end up with this feedback loop through an intermediate state. And maybe I should back up a bit and just describe a little bit what cast nodes are. They're the essential building blocks of the compiler front end. They're themselves supposedly an AST. It says so on the 10. Except it's a low-level compiler-focused design with little user-facing consideration. It's certainly not suitable for consideration as a document object model for the Raku language. So yeah, this is the base model. This is the base compiler's model of operations. And this world object ending up as a sort of intermediate state tracker for the grammar code and the actions code, so that there is enough context for the cast generating code in actions to hopefully make correct decisions as it unfolds. The outcome of this is a great deal of interwoven logic that can be quite difficult to comprehend. So this is a gratifyingly simpler generation model that exists for RakuAST. We have a mostly one-way flow from grammar to actions into RakuAST. So the the advantages here are clear from the outset. You end up with all of your logic, all of the really important logic around the creation of these nodes living in that node code itself and generating the cast in ways that once you implement a certain logic in your base class for, say, for statements, prefixes, for phasers, there's a lot of bookkeeping that just happens automatically when you create the subclass that handles just a single phaser, for instance. So I should note that there are a small number of entanglements between the grammar and actions at the moment, but these are supposed to be fixable because the yeah, the guiding principle is essentially that the grammar parses context free. Then the actions are called, which do any pre or post setup of RakuAST nodes, which then eventually generate the cast that is interpreted at runtime. So to implement, for an example, an operator, one must simply match the cast that the relevant RakuAST node generates with what the base compiler generates, and voila, the machinery of the compiler backend just works. However, cast does not need to be duplicated if we can think of an alternative implementation that produces the same or better higher level effect as the original implementation. And we'll see an example of that. So this line will be repeated on the next slide, but I wanted to highlight it here because it truly is the essence of all it takes to get into RakuAST development. It's surprisingly simple. Run tests, pick one at random, start a normal debugging process. And that's it. We could stop the talk here, but I think that would be a disservice to sharing information, to knowledge sharing, but it really is a perfectly summated line of how to get started. It's as simple, it really is as simple as this. And I did this while mostly fixing roles. So I chose not to seek out any help on the IRC channel, and I just banged my head on them for a couple weeks before reaching out for any help, and managed to get a lot of progress. And it felt a bit like dungeon delving. Yes, I'm going to make a dungeon, like a role-playing game reference. It can be quite high-paced and exciting at times as you battle monstrous bugs. These bugs, however, are almost exclusively due to missing implementation, at least until you start getting them working enough to introduce your own bugs. So some corner case lurks in the shadow, preventing your successful vanquishing of a single spec test file by some simple oversight on your part. What could it be? It's time to start plunging the depths yet further to reveal the secret. And that's how it feels on hacking on when you're down the rabbit hole, hacking on RakuAST. So here's a conversation that all started. I won't read it all out loud, but basically 9 demonstrates that the subset is not yet implemented and then gives concrete instructions. Look at the Perl 6 grammar and port that over to the Raku grammar, then add actions. So I know that might still seem a bit abstract. I know it did for me when reading it in this conversation, but reading it now, it strikes me by how it's really all there is to, for instance, adding subset. When it comes to adding a missing piece of the language, something that's not parsed properly yet, it really is just about looking at the old grammar, porting it to the new grammar, and then starting on actions. And starting on actions means developing a RakuAST node. But before you get too far ahead of that, I would like to introduce you to some helpful functions that I have developed. I use the fish shell, not as a login shell because I'm not insane, but it's the first command I run in most, or I have terminal tabs that open directly in it. But you know, caveat untoward, I don't recommend changing your login shell to fish, but using it as a tool is amazing. But that's not what this talk is about. I have a function here that sets RakuAST in that tab, of terminal tab. So not only does it export RakuAST, it sets some helper variables that I can use in my command line invocations. And then it sets the test jobs to some multiplicity equal to could be even greater than my CPU core count. And I really recommend setting this because it makes your life a lot more pleasant. And in set base here, we just do the same thing, except our version of the cast environment variable just says target equals AST. And that's because that's what the old target of AST was. Now that will give us something different, but in the base compiler that outputs cast. And yeah, this is basically the idea here is you have two tabs. One is your base and one is your RakuAST, and you compile in base because we can't currently compile core setting with RakuAST. So you're compiling in base, double testing, double checking your logic with base, and you have a tab dedicated to all your RakuAST invocations. Yeah, speaking of which, it's really worth your time, in my opinion, to set up something that'll stop you from compiling when you're in your tab that has RakuAST set, because it's just frustrating to be kind of waiting for your compilation to be done and then only to have it bail out at a failure at a relatively late stage. So yeah, I also do this make real clean thing just because sometimes things can get a little bit weird with recompiling. So for me, it's just worth the extra peace of mind. But that's kind of less important. What I do recommend trying to do is removing all of the more files from from the spec test directory, and Fish makes that super easy with their with two splats here, doing recursive matching of files. Okay, a little bit more, and we're going to be done. I have make tests here, and I find this to be really helpful to just have it. I have some regularity. They're all labeled capital A, so they're easy to see, group together, ignore, delete, all that kind of stuff. But I like to have it cleanly associated with the branch that I'm working on. And then I run a comparison script between these two things. And so make test just calls compare tests at the end. And that's just this simple Raku script. And yeah, just doing simple set math on stuff. I just really like to highlight how, a smarter person would probably just use diff dash u, but I like to have my little custom tooling around this. So I've written the same script like 5 times in different Raku repositories. Some setup they can be useful. This is the one that I wish I had implemented at the beginning. So this is R, and it will call, it only works within when I'm in the Rakudo directory itself, as it tries to call the local Rakudo M. But what it really does is it transposes an argument from the end to be a command line argument for Rakudo M. And that's really useful so that I can ask it to give me a target out AST or target cast without having to scroll all the way back through my one-liner. So this is another really highly recommended. Do something with R for yourself, some kind of alias to make it easier. And then of course I have to do an RT that doesn't use -E. So this is for the running test files primarily, but it could be used to run any script. So about once, this is an operator I was not familiar with, not an operator, statement prefix that I was not familiar with prior to implementing it. But it's kind of cool once I got the hang of it, or got over the initial shock of it existing. In this hypothetical situation, we have a logging implementation that we don't want to integrate too deeply into our worker implementation. So for instance, we would prefer not to give our worker objects a logger ID attribute, even though it needs to keep a static logger ID for its lifetime, because the entire logging infrastructure is being rethought anyway. And we don't want that to become a worker attribute. So this gives us similar semantics in that we can set something that is static for the life of the runtime. So the very first time that log gets called, the once in this case is a statement, but it could also be a block. So it's what we'll be calling blorsts, but we'll get to blorsts soon. It calls the once statement and returns that value, which can then be stored in logger ID. So every time log is called, this will be a new variable initialization, but it'll always be a static right-hand side value. Now, so we can guarantee that this logger ID is static for the life of the object. And if that reminds you of something, if that reminds you of a state variable, then good catch. It's more or less functionally equivalent to this. So how do we implement it? We add it to this grammar file. Well, this is about all that had to happen there. Then we go into actions. What do we have to do with actions? Okay, well, looks like we have to create there's this notify thing that's being called with the name of what appears to be a class. So yeah, notify creates, because we don't have these classes available in scope at this time, we kind of have to fudge it. And this creates a reference to statement : whatever's in $ name. But at the, right now it's separated. So that's the next step. So this is all we had to do for actions. So this RakuAST code is very much about producing the cast that it produces. The way that it actually works is it very much uses state, like down to the literal implementation uses the same functionality as state variables. So there are other cast generating hooks that once that this class generates, this node generates or inherits from its parent classes that are also triggered at various stages of compilation and interpretation. But or sorry, strictly of compilation. But the no, I guess with begin and check time, it gets fuzzy. We only need to concern ourselves with implementing AMPL, the expression cast. So what does this like node output when the compiler needs to know what it looks like as an expression? And what it ends up looking like as an expression is a model of how it works in the base compiler. It creates a decont op, then an if op. So if p6 state init flag is set in the call frame, then call p6 store. And okay, here we are with EMPL closure cast. So that's where the actual cast of the blorst will live. So by that point, it'll be a block that'll be called, and then the results stored in state name. Okay. And if not p6 state init, then just return the state, the variable at state name in the lexical from the lexical scope. Okay. Well, it's not so bad. And indeed, it is a lot nicer, simpler than the way it looks in the base compiler. I want to just check in about the implicit state variables that are used here, because it can be used where they're used in both the implementations that we'll be looking at today. And yeah, we have an overview of the class right here. This is all it takes to implement specifically the state, implicit state declarations. So with new, this is what NQP kind of looks like. We have to use bind attribute, and there's a string variant. So this is what it looks like to do assignment to the name variable that is part of the declaration of the parent class. So we're setting things on parent classes here until we get to the init to 0 attribute. And that's sort of basic bookkeeping, but it's important for, yeah, this is, you don't actually get to have these attributes in scope like you normally would in a Raku in a Raku class definition of, you can access your parent, any inherited attributes in that context, but here in NQP you cannot. So this is important to keep in mind. This is something interesting that's produce implicit lookups. And so when we do our init to 0, we're going to need to have a reference to the core setting version of int. So not a boot int, not an NQP level int of any kind, but a Raku int. So we need a reference to that class. So we need to create here an implicit lookup. For that int type object. Well, it's not the type object itself. It'll be it will be able to access it, as you'll see in a second. So we also need to produce a meta object for this thing. And we do it in a custom way because we want to facilitate this initialization to 0 as a completely boxed integer with a container and everything. So we get the name, the value of the name attribute there at the beginning. Then we create a container descriptor. This is an NQP level thingy, or at least not a Rakudo class level thingy, that describes the scalar container we are creating. If init to 0 is set, we store a boxed value of 0, essentially setting the container to 0 as its default value. So looking at this code today, I wonder whether there might be a RakuAST native node-based solution to doing this. Because right now it's a sort of a translation of code that exists in base actions. And yeah, it could be that using an int literal node would have done exactly the same thing that I need here, or some other construction could have resulted in the same cast that gets output. Well, this isn't even part of the cast so much as the setup of the meta objects, which are referenced by the cast. And that's how individual statements and casts are associated with various objects or blocks or any of that kind of thing. So yeah, something else there might be some other way to get this kind of set up on a container descriptor and into a container that can be used as a meta object, all that kind of stuff, possibly. But this was one way to do it. And then finally, we have IMPL cast declaration, which is called when it's time for scope to emit its local declarations. So this happens when a node does the role. Well, we don't actually have does, but some of these are roles, like RakuAST meta is a role. Or when a generated lexical declaration is added to a scope directly. So those are the two times that you'll get this cast declaration method called. And so you can see here we have the container that we got from the meta object. We ensure that it's available in the context. And then we declare a variable with that container as the value and the name that we were given in our constructor as the name attribute. So what does that actually look like? We'll see in a little bit some actual cast. I might be running really low on time. I'm not sure how much what our keep me posted if I'm running low on time. Something happened on the way after implementing once, and that's when there's something kind of weird about once in the sense that it does something kind of like a phaser, but doesn't look like a phaser. It's not defined to sort of run at any specific time. If you were wondering which one happens first, P6 state init or first happens first, which is cool. And yeah, I don't know. I enjoyed. I had to chuckle myself at the like this weird version of multiplication that I decided to use. Yeah, so basically we have here a just a small example of maybe I'm sorry, there's something broken in this output. Yeah, you're supposed to get message here. So we have a message class, and you have these two different versions. This is what you have on the right. What you see on the top right here is the base compiler behavior, and what you have below that is what RakuAST currently does. And I'm kind of putting the cart before the horse, but the point is basically that we've replicated the behavior. We've made once redundant by giving first the same semantics that it can that it has that once has. So it can now, like first was originally only targeting loops. Now you can use it for the first time a method is called, or the first time a subroutine is called. Anywhere once was usable, this will be usable too. And as you can see, it returns its value. So but before we got there, we had this initial implementation. So here I am in the middle of RakuAST blocks expression cast method, and it started to feel ugly. It didn't. It actually doesn't even work. So this did get committed because I the test case I was using. So always double check your test cases, because I was using a if while loop, like a while loop that only runs once. And then I saw that it ran once and I was like, oh, it works. And then it actually ran every single time that you called the loop. So anyway, yeah, there's not too much to get into here. We can talk about how P6 set first flag is an XStop, which is sort of like an ugly stepchild of NQP operators. And the mechanism itself is sort of a bit wobbly and not necessarily considered how we would do it if we were going to implement it today, which actually led to a great revelation by Nine, which was that what are we actually trying to achieve here? Well, we can achieve it using simply just RakuAST. So here is the overview of the first block, the first node implementation. I'm going to go quite a little bit quick. But one thing to note is that you can control when your perform begin is called. So we have is begin performed before children, true. Is it performed after children, false. So it should only ever be performed before children, before the children have their perform begin method called. So you get to choose whether you want that to have their setup to have happened already, or whether you need to take precedence over that, which I think is really nice. So this is what the perform begin actually looks like. We get the blorst attribute. We set that into the original blorst attribute, which is how we achieve round tripping through dparse and .ast. We kind of do a little bit of a cheat here. I think this should probably be going through implicit lookups, but it works as it currently works. So only Nine could clarify that. We find the attached block. That's a whole other concept. We get a trigger name. We set up a variable. We add that generated variable to the attached block's lexical declarations. So when that attached block gets asked to declare itself, it will include the implicit state. It'll call that IMPL cast decl method on this variable. And so likewise, we do the same thing with the value var. And this is sort of this is what we wrap it up in. So effectively what we're trying to do is, I think it's on this. This is what we want the code on the left-hand side. This is what the code looks like deparsed. Unless the first block has been triggered, trigger the first block and store its value in first block value. set first block trigger to true. And that's it. That's what we're trying to do here. Um, that won't work. That obviously won't work when you try to eval it again. So that's why we have the original Blorst. But if you bypass the original Blorst, that's what you get from Raku when calling it on this. Or deparse, I'm sorry. So yeah, that's basically what we do. We wrap it in the AST, and I'm so thankful for the colon dispatch variant for saving me a little bit of sanity with parentheses. It looks kind of like it would be hard to manage these, but it's much harder to manage a huge cascade of them. So at least in my editor. And yeah, then we bind that blorst into the blorst attribute, and then whenever that blorst is being queried by by the by the compiler front end for any reason, as in an expression, or then it's right there. So actually, we have we explicitly define our expression cast for this node as returning the value, the returning a reference to the variable that stores that value that's returned by the first, calling the first statement. So on the right hand side, you can see the output of. So here's the of the invocation on the left hand side, where you can see the genius of this postfixed AST variable, which really allows it to, it's so much simpler. I really wish that I had done this earlier. So I recommend doing it ahead of time. This is what the deparse looks like. I added a say once. So yeah, anyway, it's not exactly the same, but this is what the deparse looks like when it's using the original Blorst. And this is what AST generates when you call gist on it. So if you call say on the AST objects themselves. So there's kind of different representations. This is the target AST, which will always have the uncorrected long form version of the AST. Like, this is not a bug because this doesn't need to round trip. And it's actually good that when you're looking at what the compiler's really sending or getting or understanding, to actually see the fudging that we're doing, not fudging, but the implementation details. Whereas for these, you don't want those implementation details at all, because these need to be able to round trip. So this is what the cast looks like. And let's just to say that there's a big chunk of cast declaration here, stuff that's generated by IMPL cast decal. And you can see here the name of the first block triggered and first block value. And so, this AST represents what we're trying to do in its own right. But document object model, it is not. Yeah. So I said, oh, and what's nice is we were able to do this this was entirely without any reference to cast. And the solution didn't live in RakuAST block, special casing the expression cast of the block. It's happening here on the node itself. And doing it this way, it automatically works just out of the box inside of methods and subs. And so it was a simple next step to give it the return value semantics. And you can see maybe how this we can solve things in interesting ways, with in giving current problem, like given the right problem. Not everything can be done without just doing dirty cast translations from base, but some things can, and it's pretty nice. But I did have to touch one cast thing, and that was actually to remove this take first flag thing that was being attached. So this is the code that makes our block. Oh, yeah, this is the code up above that where we do IMPL callish cast. That's the stuff that makes our block call itself, which you can see here, the op call method clone, cast w val block. And in that w val is the meta object for this block. And that's how it knows which block to call. Let's see any other important details here. I think that's it. I just wanted to leave on this note. The current my goal is that hopefully after the end of this presentation, that this statement makes some sense to you. The current compiler frontend has a cast block for both its representation of a block and a thunk, and the need to thunk can be discovered later in the parse, and then it has to try and fix up the situation, which is error prone. The RakuAST based frontend models the program differently and produces the cast block nodes much later, when the thunk block shape of the program is already fixed, and so is more robust in this regard. That's basically the essence of that tension of opposites that I was trying to describe here, and what falls out of it, by by doing as much of the understanding of the what need, it's kind of weird, this idea of context-free context, but you need to give the node enough information to whatever information you have from the parsing stage. You have to give the node enough of that information to be able to make all the wise decisions about how it's going to represent itself. But once you do that, it just falls out naturally that bugs will be solved, because there's just one little less corner case, or less, or there's just less surface area for oversight, if that makes sense. So thank you all for bearing with me, and I'm open for questions if anybody has any. What is a thunk? Yes, a thunk. Yeah, it's a good question. I don't know how to exactly to explain it beyond taking an expression and wrapping it in a callable context. So when you thunk the expression 5, you get a sort of like a smart match. It's not automatically a smart match, but you get it when the way it works for where clauses is, it is a smart match. So if you say where 5, you get a where star smart match is 5, right? That's the thunked version. But you have curry thunks, which are the underlying nodes that hold your the fact that the RakuAST node, the apply infix node that you're working with, has been thunked. That means that that mean curry thunked. That means it has um sorry, my brain's a bit fried from all the presentation, but the that means it has been that whatever code was encountered, and that expression has been turned into an executable. Not into an executable in that sense, but it is now a callable piece of code that lives there with an argument and a signature and everything.
Maybe I can help.
Yeah.
Say something like say or dot say for $5. The dot say actually has its dollar underscore localized, but it's not the dollar underscore that's around it. It's basically become that thunk that you have on the left side of the for. That's a thunk. It looks like it's a statement, but it's actually a little bit of a block when it actually executes.
Very cool. Thank you.
Right?
All right. Any other? Yeah, that's some stuff that you get used to when you're hanging out in the core is blorsts and thunks. I thought we were going to get more into blorst, but that it's a blocker statement is a blorst. And you can have statement prefixes, for instance, takes, blocks, or statements. So a lot of things will take a block or a statement, and then you have blorsts. And blorsts can be thunked because any expression can be thunked. So, all right, thank you very much for your time and everybody's presentation so far in the conference. Really enjoying it.
Yeah, thank you. Thanks indeed. And
actually, wait, Rafe said he had a question. I'm sorry.
Okay.
I think it says he's Griston Gray. That's a RakuAST just and say. Was that your question? I don't have a strong opinion on that.
I have a thought on that. If the plan is to switch over to AST in the next release, whenever that is, introducing methods to then take them away doesn't seem great.
You mean introducing ones to take it away?
Adding new ones now that specifically work with AST when eventually the default is AST and then the other option won't be available, then we have two methods doing the same thing.
So this is in response to Rafe's comment, right?
Yes, the thing that we were just talking about.
Yeah. Okay. Yeah, I don't. Yeah. Thank you for sharing.